Hello everyone, welcome to the Fundamentals of Analog Electronic Technology class. I will continue to explain analog integrated circuits to you. In the previous lesson, we studied DC biasing techniques in integrated circuits. In this lesson, we will study another important topic, the differential amplifier circuit. Differential amplification is another important building block of analog integrated circuits. In this lesson, there are two main knowledge points: the general structure of a differential amplifier circuit, the FET differential amplifier circuit. General structure of a differential amplifier circuit. As shown in the figure, a differential amplifier circuit is composed of two identical three-terminal devices, either FETs or BJTs, T1 and T2. The input terminals of the two devices are connected to the input signals V sub I1 and V sub I2, respectively. A differential amplifier processes signals composed of a differential mode signal and a common mode signal. From the circuit diagram, we can see that V sub ID equals V sub I1 minus V sub I2. V sub IC equals V sub I1 plus V sub I2 divided by 2. Therefore, any two input signals V sub I1 and V sub I2 can be expressed as V sub I2 equals V sub IC plus 1 half V sub ID. V sub I1 equals V sub IC minus 1 half V sub ID. We can conclude that the common mode signals of the two inputs are equal in magnitude and identical in polarity, while the differential mode signals are equal in magnitude but opposite in polarity. That is, the common mode signal corresponds to the identical part of the two input signals, and the differential mode signal corresponds to the different part of the two input signals. Now let us study some performance parameters of differential amplifier circuits. V sub ID equals V sub I1 minus V sub I2. This is the differential mode signal. V sub IC equals V sub I1 plus V sub I2 divided by 2. This is the common mode signal. A sub VD equals VO prime divided by V sub ID. This is the differential mode voltage gain. A sub VC equals VO prime divided by V sub IC. This is the common mode voltage gain. Here, VO prime is the output produced by the differential mode signal, and VO double prime is the output produced by the common mode signal. The total output voltage is VO equals VO prime plus VO double prime equals A sub VD times V sub ID plus A sub VC times V sub IC. The common mode rejection ratio, K sub CMR, is defined as K sub CMR equals the absolute value of A sub VD divided by A sub VC. It reflects the ability to suppress zero drift. Zero drift refers to a phenomenon in which, when the input signal is 0, the output voltage is not 0 and changes slowly over time. There are two causes of zero drift: temperature variations and fluctuations in the power supply voltage. We will analyze the output of the differential amplifier circuit and its zero drift suppression in detail later. Now let us study the FET differential amplifier circuit. As shown in the figure, two identical enhancement type NMOS transistors, T1 and T2, are used to form a source-coupled differential amplifier circuit. From the figure, we can see that the sources of the two transistors are connected together and share the same current source I/O. Therefore, this is called a source-coupled differential amplifier circuit. First, we perform a static analysis of the circuit. The static circuit diagram is as shown. In the static state, there is no input signal, i.e., V sub I1 equals V sub I2 equals 0. We first assume that the circuit operates in the saturation region. Because the circuit is completely symmetrical, we can obtain I sub D1Q equals I sub D2Q equals I sub DQ equals 1/2 I sub O V sub GS1Q equals V sub GS2Q equals V sub GSQ. From the equation, I sub dq equals k sub n times v sub gsq minus v sub tn to the power of 2, we can further calculate v sub gsq. V sub ds1 equals v sub ds2 equals v sub d1 minus v sub s1 equals v sub dd minus I sub dq times r sub d1 minus negative v sub gsq. Once the static operating point is determined, we need to verify whether the circuit is indeed operating in the saturation region. If the assumption holds, we proceed to the dynamic analysis. First, we apply only a differential mode signal, with V sub I1 and V sub I2 equal in magnitude but opposite in phase. VO1 and VO2 will be equal in magnitude but opposite in phase. VO equals VO1 minus VO2 is not equal to 0, meaning the signal is amplified. Next, we apply only a common mode signal, with V sub I1 and V sub I2 equal in magnitude and in phase. VO1 and VO2 will be equal in magnitude and in phase. VO equals VO1 minus VO2 equals 0, meaning there is no signal output in the differential output mode. In practice, even with single-ended output, the circuit has strong common mode signal suppression capability. Principle of zero drift suppression. In a differential amplifier circuit, whether due to temperature changes or power supply voltage fluctuations, both transistor drain currents and voltages will change. This effect is equivalent to adding a common mode signal voltage to both inputs. In the ideal case of differential dual-ended output, the output voltage remains unchanged. The common mode output voltage is 0, and zero drift is suppressed. Calculation of main parameters. Differential mode case. 1. Dual input, dual output. V sub I1 and V sub I2 will be equal in magnitude, but opposite in phase. The increase in I sub D1 equals a decrease in I sub D2, or vice versa. The current to the common source branch remains unchanged, meaning the potential at the common source node S does not change. This is equivalent to the AC potential at node S being 0, i.e., V sub S equals 0. Thus, we obtain the AC equivalent circuit shown in the figure, with dual-ended output connected to the load. The circuit is completely symmetrical, equivalent to each side having half of the grounded load. Voltage gain. A sub VD equals VO divided by V sub ID equals VO1 minus VO2 divided by V sub I1 minus V sub I2 equals 2 VO1 divided by 2 V sub I1 equals VO1 divided by V sub I1, which equals the single-ended voltage gain. In a fully symmetrical circuit with differential input and differential output, the differential mode voltage gain is the same as the single-ended voltage gain. It can thus be seen that this circuit uses a multiple of the components in exchange for the ability to suppress common mode signals. 2. Dual input, single output. As shown in the figure, if the output voltage is taken from the drain of one transistor, VO1 or VO2, it is called single-ended output. The voltage gain is only half of that in the dual-ended output case. 3. Single input, single output. According to the superposition principle, when the excitation source on the left is set to 0, the circuit is equivalent to dual-ended input for the left excitation source. The signal applied to both inputs is equivalent to a common mode signal V sub IC. Here, we consider only the differential mode signal, so the differential mode case is equivalent to dual-ended input. the differential mode parameters are the same as in the dual-ended input case. Common mode case. Since the common mode signal means the same signal is applied to both inputs, we do not distinguish between dual-ended or single-ended input. 1. Dual-ended output. The common mode signal input causes the drain voltages of both transistors to change in the same way. So the common mode gain, A sub BC equals V sub OC divided by V sub IC, is approximately 0. 2. Single-ended output. A sub EC1 equals V sub OC1 divided by V sub IC equals V sub OC2 divided by V sub IC equals negative G sub M divided by 1 plus G sub M times 2 R sub O is approximately equal to negative R sub D divided by 2 R sub O. From this, we can see that the common mode voltage gain is approximately RD divided by twice the output resistance. That is, the larger the output resistance, the closer the current source is to the ideal case, and the smaller the common mode voltage gain. The common mode rejection ratio, K sub CMR, is defined as the absolute value of the ratio of the differential mode gain to the common mode gain, as shown in the figure. For dual-ended output, ideally K sub CMR equals infinity. For single-ended output, K sub CMR is approximately equal to G sub M times R sub O. The larger the K sub CMR, the stronger the ability to suppress zero drift. When designing an amplifier circuit to amplify the differential mode signal and suppress the common mode signal, the common mode rejection ratio must be at least greater than the ratio of the common mode signal to the differential mode signal. Otherwise, the signal component in the circuit output will risk being overwhelmed by drift and other interference. Everyone, in this lesson, we have studied the differential amplifier circuit, including the general structure of differential amplification and the performance parameters of the FET differential amplifier circuit. The content is substantial, and you should practice diligently after class. That concludes our content for today. See you in the next class.